Hello and welcome back. So what I want to talk to you about today is the comb generator. It's a really basic type of signal generator that has quite a lot of uses. On the one side in high frequency radio applications, so stuff going up into microwave territory, but it's also a very useful tool in EMC applications, where it's used as a well-calibrated and well-known noise source. Now, this is a circuit that's quite easy to make, and it will be able to generate signals up into the gigahertz range without too much hassle, but it will always generate multiple frequencies at the same time, frequencies being harmonics of a fundamental frequency. So basically, it's as complicated and as useful as your calibration output from your oscilloscope. You don't use it all the time, but when you need it, you need it. So, if you're curious what this thing is, how it works and how you can build one, then keep watching. So, to start things off and to understand how the comb generator works, first we need to remember some fundamental signal analysis concepts. For example, a square wave can be expressed as a sum of fundamental sine waves, with the main property that the frequency of the sine waves is a multiple of the frequency of your square wave. So for example, a 1 kHz square wave can be built up from sine waves having 1 kHz, 2 kHz, 3, 4, 5 and so on. So it's only integer value multiples of the original frequency. Now the exact amount of each of these fundamental frequencies, so what the exact coefficient for each of them is, depends on two main factors of your square wave. On the one side, it's your rise and fall times, so how sharply the square wave actually switches. So from this point of view, we look at the square wave not as a square wave, but rather as a trapezoid shape. And the second important parameter is the duty cycle of the square wave. So the ratio of on time to the period. For example, if you have a perfect 50% duty cycle square wave, one of the consequences of this will be that the square wave will be built up of only odd number frequencies. So for your 1 kHz 50% duty cycle square wave, you need 1 kHz sine wave, 3 kHz, 5 kHz and so on. You have no content from the even number, so from 2, 4, 6 and so on. But on the other hand, if the duty cycle is something different, so more or less than 50%, then you will have all of these frequency multiples. Now, to get a better understanding and a better feeling of how this works, let's look at this phenomenon in a simulation. LT-Spice, of course. And for that, what I got here is a few signal sources. So on the one side, I want to look at how duty cycle will affect the spectrum, and on the other, how the transition times. And for that, of course, I will be using the FFT function of LT-Spice. So if we run this thing, first let's look at duty cycle influence. I'll simply view this data as an FFT, and just to make things a bit more clear, I will set the window to linear view. Now at the moment this looks like a mess, so we can split it into three different plot planes. So now we can see on our 50% duty cycle, so the first one, that we have our fundamental at around 5 MHz. We don't have the first harmonic, so at 10 MHz. We have our third, 15 MHz, 20 is not there, 25 again, so we only have the odd frequencies, 1, 3, 5 and so on. But if we look at the other spectra, so the 33% or the 20% duty cycle, we have our fundamental at 5, we have a spike at 10 MHz, then at 15 and at 20. We don't really have one at 25 and so on. So the spectra will depend on the exact duty cycle. Normally in comb generators, what you use is 50% because it's easiest to obtain and it's easiest to control. Now, the second thing we can look at is how the transition time is influencing the spectra. So what I have here is three waveforms, one that has a rise and fall time of 10 nanoseconds, one has it at 2 nanoseconds and one has it at 500 picoseconds. So again, if we open up the FFT window and set to linear and split everything up into 3 plot planes, we can see that with slow transition time, so the 10 nanoseconds, we have quite weak harmonics, so the amplitude drops off really fast. When we decrease the transition time to 2 nanoseconds, we start to have a bit of a broader spectrum, but this again drops off, whereas the 500 picoseconds, so the fastest one, has the broadest spectrum. Now you may have figured it out by now, but the term comb generator comes from the fact that the spectrum of this sort of generator looks like a comb. So you have a lot of spikes equally spaced and with somewhat constant amplitude. And from this we can already see that to get this sort of spectra we need a clearly defined frequency, so we need some sort of square wave generator, but we also need very fast transition times. So normally you will be using some sort of crystal oscillator, so you can use one of these things, so it already has the quartz crystal and the oscillator all built into the same package. This is what I will be using today, but this thing doesn't have that fast of a rise and fall time. So we have somewhere in the order of 5 to 10 nanoseconds or a bit less depending on how much loading there is on the output. But how do you get faster transition times? How do you get below the 1 nanosecond mark? Well, for that we need to turn to the whiteboard again. So when you want to rectify a signal, say a sine wave using a semiconductor diode, especially a PN junction type, what you expect is to get something like this. So you have only half of the signal passing through and you don't really get the other half. But the behavior is not that perfect. There is a bit of an imperfection right when you go from conduction to non-conduction. Now I tried to make a little zoom in here on this little point, and basically what happens is that to get the diode conducting, you need your charge carriers to combine in the junction so that current can pass through. So you got your holes and your electrons combining and current passes through the diode. Now, when you reverse the voltage, those charge carriers don't immediately disappear from the junction. It takes the time it takes for the diode to stop conducting current. And that's exactly what happens when you go from a positive to a negative voltage. For a very short amount of time, the diode will be conducting the other way. And the time it takes for the diode to stop conducting is called the reverse recovery time. And based on how much capacity the diode junction has, the transition from conduction to non-conduction will be more or less sharp. So for low capacity radio frequency diodes, you can get very sharp transitions by taking advantage of this effect. And if you want really fast transition times, you have special step recovery type diodes. And this is exactly the effect that you need to get your comb generator to have a very broad spectra. And to show off this effect, I prepared a few schematics in LTSpice. So this will be the reference circuit that we start off with. We have a basic signal source that has quite slow transition, so 10 nanoseconds rise and fall time. I added an AC coupling capacitor, 100 picofarads. You will always need this sort of capacitor in such a circuit. And I'm driving the signal into a 50 ohm load. And if we look at the output, well, it's quite a slow signal. So we see our output signal having transition times in the order of the base signal. So to take advantage of the diode's reverse recovery, first of all we need to add a diode into the circuit. This circuit doesn't have a diode. And we also need to get the current to go through the diode and then to reverse polarize the diode. And there's two main ways of doing this. On the one side, connecting diodes to ground, and on the other, connecting diodes in series with the signal. So if we start off with the version in which we connect diodes to ground, for this simulation I'm using the 1N4148 diode, and if we look at the output of this circuit and compare it to the initial one, well, not much has changed. We got our 0.7 volt conduction voltage limitation, but other than that, the switching times are roughly the same. Now, if we look at the diodes and we look at the current through them, we can see that we do get our reverse recovery conduction. So we see current going forward through the diode, and then we have current going also the other way. And the transition between the two is extremely sharp. So we have hundreds of picoseconds of fall time here. But we don't see this in the voltage. And the main reason for that is that I'm using fairly ideal components. So my signal source has no series resistance, and my capacitor again has no series resistance or inductance. So when we have a sharp current transition through the diode, there's no component on which you can get this current to voltage transformation. But if we add an inductor in series, so just 100 nanohenries, we have a completely different waveform. So now we can see when the diode goes from conduction to reverse conduction, we have an extremely sharp and abrupt signal transition. So we have our few hundred picoseconds of transition, and we see this in the output voltage. So when you're using diodes connected to ground, you can add either series inductors or series resistance, or just rely on the layout parasitics. And that will turn this sudden current transition into a sudden voltage transition. But the way in which I got the circuit to actually work involves placing the diode in series. So another way to build this thing looks something like this. You got your same signal source, got your diode in series, and then this couples through a capacitor to the output. Now, of course, there are also some other kinds of implementations, but I will concentrate on this one. So basically what we have here, we have the same input signal. We see this signal almost unaffected at the input of the diode, and on the other side of the diode, we have a voltage around 2 volts. So we can get the diode conducting in a forward manner. So we have our nice 0.7 volt drop on the diode, but then we also have this reverse polarization of the diode of about 2 volts. So we have all the conditions necessary to get the diode to reverse conduct. And that reverse conduction happens at exactly this moment. So if we look on the voltage plot, we see that we have our nice few hundred picoseconds of rise time. We also have a bit of ringing. This has to do with the inductor placed at the beginning, whose exact value will depend on the exact diode. But the point is that by building this sort of circuit, we can get quite a nice spectrum full of harmonics. So, enough simulations, let's see how this thing actually works in real life. And for that, I prepared a little board. It's quite a really simple circuit. What I got is a simple 3-volt battery, so a CR2032, a switch, an LED to show that, well, there's still voltage in the battery, a crystal oscillator, so it's not just a quartz crystal, it's an oscillator at 12 MHz. I had this thing lying around, with a decoupling capacitor, and then on the output we have the inductor, diode, resistor connection to ground, series capacitor, and then the output RF connector. I also left space for this resistor, but I didn't really use it. From a layout point of view, again, a tiny little board, as simple as possible, came out nice and compact. And well, let's see how it works. So, first of all, to check the waveform, I got this setup here. So this is the board. It's connected to the first channel of the oscilloscope, and I also have my 50 ohm termination added on this bunch of B and C connectors because the oscilloscope doesn't have one, so the oscilloscope has an 1 mega ohm input, and I added the 50 ohms externally. So if we fire this thing up, I have a 20 nanosecond per division setting at the moment, and we see this waveform. It doesn't look exactly like the one we saw in the simulation. So the oscilloscope is measuring about 7.4 nanoseconds of transition time here, but that's most likely because of the oscilloscope's bandwidth limitation. So this is a 70 MHz oscilloscope, and to clearly see what's going on here, this is not the best tool. A better tool would either be a very high bandwidth oscilloscope, so something in the 1-2 GHz range, or a spectrum analyzer, a tool that will actually show us the spectrum of the signal that is coming out of my signal generator. And today, what I'll be using is this thing. This is one of these heterodyne spectrum analyzer thingies. You can get them quite cheaply for like $50 or so. But keep in mind that you get what you paid for. So let's check out the spectrum of my circuit using this thing. So first things first, I short-circuited my diode so that we can see the spectrum of the signal that we're starting off with. No point in making a complicated circuit if you already have enough harmonics. And I have this connected directly to the input of the spectrum analyzer. No extra resistors were added this time because the spectrum analyzer already has a 50 ohm input. So cover this thing up to prevent any extra noise getting in, and let's see what the spectrum looks like. So what I'm measuring here is the spectrum from 40 MHz up to 1 GHz. We can see our nice harmonics, and we can see that even without adding any extra circuitry, we have spikes going up until around 800 MHz, and then some other things that are quite barely visible because of the sensitivity of the device. Now if we play around with the cursor function, we can see our spikes at 24 MHz intervals. So the oscillator is running at 12 MHz, but we only see even harmonics, so we see the 12, which is not really present here because the circuit can't go that low. Then the 24 is missing. Then we have our 36, which again is too low. 48 again is missing, and then the first harmonic should be at 60. And we see it at 60.07. Then the next one at 72 is missing, and the next spike is at 84. So 83.78, it's 84. So now we know what we start off with. Let's start adding diodes. And there's two diodes I want to test today. The 1N4148 and another BAT216. And if we check this diode, we see that the spectrum is changing, and we start getting some extra harmonics above 700 MHz. So we do see the reverse recovery effect of the diode in action. We have a bunch of these extra spikes also at the even frequencies, and we also have these going up until the 800-900 MHz range. So if I simply extend our frequency range to 1300 MHz and wait, we see our harmonics stopping just shy of 1 GHz. But now let's test a better diode. The main difference between the 1N4148 diode and the other one refers to this diode capacity parameter. So with the 1N4148 we had a maximum of 4 picofarads, whereas the bus 216 has a maximum capacity of 1.5 picofarads. So it's almost 4 times lower in capacity. And by adding this thing, if we rerun the measurement, we see again some of the spikes changing, also from lower frequencies. But we also see the spectrum slowly changing, so we see some spikes going on even later, so above 1 GHz. Now of course some of the spikes are below the measurement threshold of the spectrum analyzer, but if I would have an extra amplifier added, then we would see much more clearly the effect of these diodes added as step recovery components. So all in all, a proper cone generator is a far more complex circuit than this. You also need an amplifier circuit, you will need some voltage stabilizers, maybe battery management if you want to run it from a rechargeable battery, but it's quite a useful tool, both for checking equipment and as a noise source. So you can use it to check your radiated measurement setup or your conducted measurement setup, because you will always know what the emission spectrum of this thing is, but it's also useful for all sorts of other experiments. And if you use the right components, you can get harmonics well above 2-3 GHz with this thing. So all in all, hope you got some useful information out of this. Leave your thoughts in the comments. Thank you for watching. Make sure to subscribe to be up to date with all my latest videos, and see you next time. Bye bye.